Okay. Good afternoon, everybody, and thank you for having me here. I'm Suman Banerjee from the University of Wisconsin-Madison, and it's a pleasure to be visiting you all. I am here in Paris for the next few months. I started my sabbatical, actually, so it's a really exciting time, and really enjoying my stay here. So today I will tell you a little bit about some of the projects that I've been doing at Wisconsin, and there are some very interesting discussions in this space that still continues to happen, and I think is an interesting topic in its own right. So I call this broadly the roaming edge, okay, and I will explain what I mean by that. So we are all sort of familiar, I think, with the notion of edge computing nowadays. Typically we think of there is cloud-based infrastructure, usually data centers that host computing somewhere. And then you have your network infrastructure that spreads far and wide. And you can imagine lots of people are focusing on edge computing, where you bring some of the computing from the cloud to the edges of a network infrastructure. And different applications have leveraged edge in a different way. For example, if you look at companies like Netflix and others, they are trying to use more servers that are closer to the clients inside edge networks and are using them to serve content from a greater proximity to the clients. There are a lot of research, including some in my group, where we have looked at turning base stations into edge compute platforms. And that has its own unique advantages, because if you can put computation right at the last hop with the wireless link, you can do very interesting things. In fact, we have made the home Wi-Fi router into an edge compute platform, and that has its own interesting applications in smart home environments and so on. And that's a talk in itself that I'm happy to discuss offline. But today I'm going to focus on what I call the roaming edge. And the roaming edge here is essentially computing services that sit in highly mobile scenarios, especially vehicles. And the big issue, and one may think of these as really the endpoints and therefore not the edge. But the reason I call them the roaming edge is that I'll be talking about putting computing capabilities inside vehicles. Of course, if you think about it, vehicles today have a lot of compute capabilities. Because they manage a lot of interesting systems within the vehicle. But when I talk about the roaming edge, I'm talking about a somewhat of a general purpose computer environment that we are familiar with, and use it as a mechanism to populate new services for vehicular scenarios or transportation scenarios. So that's what I'm going to call the roaming edge. Okay? And I think the way to distinguish from existing computation capabilities in vehicles is that many of them are very single-purpose solutions, or they're not open. And I'm going to talk about platform that allows us to be a little bit open and allows us to deploy new services in a very interesting way inside vehicles, and that can have very interesting applications. There will be sort of, let's imagine, gateways that sit in vehicles, and the usual challenges of edge, of course, exist. But sort of some of the new challenges that come up, and you'll see the examples, obviously have to do with connectivity and reliability. When you're using these edge gateways in vehicles to do things, let's say collect data, disseminate data, make some decisions, they will be connected to the internet, but of course your links are going to be a little bit less robust, and connectivity will be an issue. Data volumes will become a problem if you are trying to, for example, use it for a lot of sensing applications. The volume of data you will collect can be very large, and it may not be possible to upload everything. This is partly why we justify the need for having an edge compute capability, because you want to process certain things effectively. And given we will be doing a lot of even audiovisual data collection, there is interesting topics around privacy that obviously needs to be addressed in this context. Okay, and what we are envisioning is that this platform, this edge platform that we'll put in vehicles, will support multi-tenancy. So it's possible that somebody comes up with an application that sits in that gateway, and somebody else, another third-party provider, comes up with another application that also sits in the edge gateway, and they coexist, they share some sensing, sense data that comes to it and makes its own judgment and does other things. So it's a multi-tenant environment that we are proposing to incorporate into this world. In fact, this is part of a very big umbrella project we have in Wisconsin that is kind of getting very interesting, and there's a lot of other faculty that are looking at different pieces of this big puzzle. And I'll talk about some of the applications that we are kind of building with this, and of course it drives a lot of interesting research on how the system should be designed, what are the requirements, and so on. Okay. So I have been working a lot in sort of smart transportation-like applications with the Edge platform nowadays. There are lots of collaborations we have developed. I work a lot closely with our local metro operator, a metro transit operator. So we have maybe 250 city buses in Madison, Wisconsin. Some of them have our edge gateways placed in them. And with them, we do things like understand where are the parking spots in the city using cameras and analytics that run locally, right? You can essentially take continuous imagery, or you can do some other techniques like ultrasound or radar to figure out, are these parking spots available or not? And as the buses go by these spots, you can learn about them in real time and share it with whoever needs that information. You can use, again, cameras for accident investigation. In fact, if you think about it, lots of transit systems, you go around the world anywhere, you'll find that transit systems are already doing a lot of video data collection, right? So like a typical bus in Madison, I know, and probably true for most cities, they have like 8 cameras on the bus, some inside, some outside. They're collecting video all the time. Now, of course, they're not connected. At least today, they're not connected. So they essentially take all that video, they store it on a hard drive on the bus. And of course, on demand, if there is an incident, somebody needs to go physically and pull that drive and look at what happened. Not a very scalable way to do things. So if we provide the right capabilities of computing and analytics on the platform, I think it can become a lot more powerful in the way you can do various kinds of incident management. There's a project I'll talk about which is related to understanding driving behavior. So how do you understand how well a person is driving? And there's lots of activity in this space. And again, we're using an edge platform to do some of that from within the vehicle to better serve various applications. Applications could be in improving a person's driving actions. It could, of course, tie to insurance. It could have other implications as well. Okay. So the platform we are building is this is the ecosystem of our platform. The heart of it is this gateway that my group has been developing. We call this gateway Paradrop. That's a name we've given it. It essentially uses sort of a glorified Wi-Fi access point, beefed up to have some GPU capabilities on it. And then the software platform on top of it allows you to instantiate containers on demand. Okay, so I'm assuming that you have at least seen or heard of use of containers. So we can enable a third-party developer to deploy these containers. We use Docker. So you can deploy these Docker containers with code, and they will get dropped onto these gateways, and you can do whatever you need to do. And the name Paradrop is sort of the mental image that you can paradrop these containers on demand based on whatever application you're running. Now, that's the platform we have been using for home applications a lot, right? So for example, let's say some third-party developer decides to come up with a very privacy-preserving security camera system where the video from the camera doesn't have to go to the cloud, but it sits locally on your gateway, and you do your processing there, and then only interesting events get sent to the homeowners or whatever, right? So you're not shipping all the video to the cloud, which is probably true for many such security cameras today. So what they will do is they will work with our platform. They will create we call these containers, in our terminology, we call them chutes or parachutes, chutes. So you create a chute, which is a specific container with your code, which does face recognition and all this other stuff. And you drop it into the appropriate gateway that talks to the security camera, and you have this whole process local, And so we have instantiated this entire ecosystem and environment. So that's Paradrop. We have augmented it to work with many different wireless interfaces. We, of course, advertise Wi-Fi. We have Bluetooth connectivity and Zigbee connectivity. And then it can connect to multiple cellular networks. That's actually some extension we did based on another project we have called Wirover, which is essentially aggregates data over multiple cellular networks so that it provides a better, more robust connectivity. And we have found it to be very useful in scenarios where one network's performance in certain locations are not as good, and so aggregation really helps in many interesting ways. So that's sort of what we already had. And then for enabling this vehicular ecosystem, we are kind of trying to embed a lot of sensors that talk to these gateways, and then have added a GPU capability on top of it, so that we can do some interesting processing in this platform. So these are just a list of some of the sensors that we have embedded. We have environmental sensors of different types. We have, you can pick and choose whatever you need for your application, but we have used LiDARs and ultrasonic rangers. Obviously, we have IMU sensors. That's pretty common. You can even put a phone and that connects and gives you IMU data. And microphone and camera arrays. So we can place multiple cameras and they stream to the gateway, and then you can do local processing to do different things. Okay, so that's sort of the ecosystem we are developing. And this is kind of, it allows you to do a lot of things. So depending on the application, you pick what you need. Okay, so I'll give you a few examples of applications we have developed and illustrate where we are headed with this. And some of this is obviously work in progress. And if you have interest and want to discuss more with me, I'll be more than happy to engage with you guys. Okay. So one of the first things we have been working on for a while is understanding driving behavior, right? This is actually very important. Worldwide, US probably is pretty notorious because everybody loves to drive and not take the public transport. And then people get very frustrated on the roads, especially in big cities, because you're stuck in traffic and you're cutting people off and everybody's getting very rude and all that, right? And there are applications out there. These are simple mobile apps you download, and what they will do is they will look at the IMU data that's coming out of your phone. It will annotate things like how you accelerate and how you brake. And from that, it can basically, you have sort of data like this. On the x-axis you have time, y-axis you have speed, and you can observe various patterns of acceleration and braking. You can observe things like turning. And from that, you can give some scores. You can say, oh, that was a bad, harsh braking. You shouldn't be doing that, and so you get penalized. And so you can build the scoring systems, and you can attribute some driver rating through this method. Okay, and similarly, this is braking. You can similarly do changes, lane changes by looking at angular speed using gyroscopes and other kind of sensors in the phone. Okay. Now, what we have realized, so we built an app like this. We called it DriveSense. Then we got into some trademark issues because somebody else wanted to use DriveSense and we didn't have it, so we are changing the name. But we collected a lot of data with it. And one thing we realized is that IMU sensors are good at providing sort of analytics on what motions happen during a drive, right? You braked, you accelerated, you turned. We can collect that reasonably well. But it does not help us understand why the driver did a certain action. Yeah, this is kind of obvious. A person could have braked very hard because a kid suddenly jumped out of nowhere with a bicycle in front of you, and by braking hard, you actually did the right thing. That's the right action because this was not expected and you did it. Or you could have braked hard because you were totally distracted looking at your phone, eating your food, and suddenly realized the car in front had already stopped and you were not paying attention. Okay? So these two scenarios are different, and just saying you did a hard brake and so you should lose some points is kind of inaccurate. So essentially, the big thing that we are trying to do is to use our platform to do driving analytics using audio-visual data that we potentially can gather from this system. And of course, these sensors can help in many ways. I mean, you could even imagine augmenting drivers' understanding because a camera or a LiDAR-based system can pick out certain objects much better than a human eye can, depending on road conditions. And so it can be used in many interesting ways, but we are currently focusing on looking at how we can better do driving analytics in this ecosystem. So, the way this can work is, first, we use the motion sensors, okay? So when you're driving on the road, any interesting activity from the perspective of driving will usually be related to some acceleration, of some kind, whether it's positive or negative, whether it's angular or not, right? If you are going at a constant velocity or something, nothing interesting is happening from the driving perspective, right? So the motion sensors still are very relevant. We still collect those data. And then whenever there are certain interesting events, like you accelerated in a certain way, braked or turned or things like that, which we can annotate, the video or the audiovisual feed around that point is of interest to us. Anything else is not of interest to us. So essentially, it allows us to discard a whole lot of video analytics that would otherwise be necessary. Okay? So we essentially use the IMU sensor data to feed what to analyze. And then we do analytics, and then we use that to combine it with the IMU sensor data to augment our motion detection and actions that are happening to evaluate driving behavior. So that's sort of our story. So we have a full system that we have developed where we use phones for event detection of different types. We have placed a bunch of cameras, and I'll show you a few examples, where we are observing things like your blind spots, looking at the driver, are you doing the right actions? And of course, we are using the audio monitoring, audio recording to detect whether you're doing turn signals or not. Of course, this depends on individual vehicles and what they do. Typically when you put the turn signal on, there is a sound as well as a blinking light inside the vehicle that you can detect. If certain vehicles don't do that, you have to train it according to what the vehicle may do. The other thing is, like when you're making a lane change, you have to, in principle, look at the blind spot to see whether you checked your vehicle's presence over there. Now, again, depending on the vehicle, this may not be necessary. Sometimes, like, the new vehicles come with a built-in camera, so you can look at the blind spot by looking at your camera as opposed to looking over there. But even that, if I can train the system, I can check whether you looked at your camera feed to ensure there was no vehicle, right? So all of these can be developed, and from that, we can really learn how well a person is driving the vehicle as we go over time. And so this is an interesting application of edge computing on the vehicle or in the roaming edge, because if you imagine, if you have 4 to 6 cameras like this, it immediately generates large volumes of data. And some people have asked, why can't you just offload all this data and then analyze in the cloud? Why do you need all this fancy computing in the edge? But you can imagine if you have a vehicle that's on the road all the time, you're either shipping all this data over expensive networks, which you're today we have to pay a certain fee based on usage, and that's expensive. And this is not a small little bits of streams of data. These are large amounts of video data that you have to analyze. So, and if the vehicle stays on the road, you cannot do that with the network speeds we have. I mean, especially in rural Wisconsin, networks are not great all the time. So you really have no choice but to analyze the data in place, and then you have to do it really in real time, because the moment you let data sit and get loaded into your hard drive, at some point your disk will run over and you will not be able to analyze. Okay, so this really made us kind of think of how to design a real-time pipeline for doing this analytics of video data, and then use it for various kinds of driving analytics, right? So, of course, one could say that another reason I need real-time analytics is to provide direct feedback to the driver. How you present the data and the feedback, that's a different issue. We have not really looked into that. But I think even without that, you still need real-time analytics just to deal with the data volume. Otherwise, you have no hope of doing this in an effective way. So we have augmented our platform with, as I said, our gateway is augmented with the NVIDIA Jetson TX2, for GPU processing of video data. And we have developed a pipeline using CNNs to do certain kinds of analytics. We have used different cameras and phones. So it's a very interesting system. And to give you a flavor of the kinds of things we have done, we do usual things like face detection, head pose estimation to know where you're looking at and what your eyes are looking at, detect objects in blind spots. Now, if you think about it, these are systems, if you think of autonomous vehicles, right? They have sort of done this for a while, and they have been successful at doing this for a long time. And so one may wonder what's new here. Well, I think what we are trying to focus on is a little more general purpose platform on which different applications can reside. And more importantly, we are trying to look at sort of solutions that may not be, that provide a different perspective to what's happening within the vehicle. So autonomous systems have to be incredibly accurate. You cannot approximately guess who's there. You cannot approximately do certain things. You have to do it exactly right. So most of these autonomous vehicles, the entire ecosystem of hardware and capabilities you need to put are fairly expensive, fairly high-end, fairly intense in terms of their accuracy. The kind of systems we are developing, at least, they are a lot more lower end. You can, of course, live with some errors. You don't have to catch every time a person turned their head. You miss a few. We are doing drive analytics, and it doesn't have to be as high-end as, say, an ecosystem of autonomous vehicle needs to be. So essentially, we can create this drive analytics capability with maybe a few thousands of dollars or so, even less, maybe $1,000, and we can build this whole thing. You don't need to retrofit a vehicle with $100,000 or more, which you need for an autonomous vehicle. Of course, our goals are different, right? So I think that's something that I should mention. And then we do all these other usual things, detect objects of different types, vehicles, pedestrians, and so on. Okay. So for example, here is what a system will look like as this is an online system. As the vehicle's driving, it detects, it defines what is a collision zone. It detects things like cyclists and vehicles and traffic lights and speed signs. I mean, again, these are things that an autonomous vehicle will do today, but this is what's running in our sort of modest compute platform with these relatively modest sensors. They're not very expensive, and you can then kind of infer what is it that the driver is doing right or wrong in this environment. Okay, so this is another example. This is an airport area in Madison, and you can see some of the things that it's picking up. Okay. So here is another example. Again, we take existing applications like face detection algorithms, and here we are kind of looking at a person's face, the driver's face, and observing where the person is looking and when the person's turning their head or not turning their head. So from that, we can infer a lot of useful information about how a person drives. And then we have built this decision tree model for driving behavior evaluation, and we have come up with various rules on what should a right turn look like, what should a left turn look like, what should a lane change look like, and then obviously check for certain things whether you did iteration you're trying to apply. That determines how much fuel essentially you're going to consume. So this is actually a kind of a tractable computation solvable problem, and this decision is run in our edge computing platform, right? So we create this table, which is a model that is available offline. Equations, and then it becomes a dynamic programming like formulation that allows us to say, to go from here to there, what step should I take? Okay, so this is the computation that runs on the edge, and obviously has to run in real time because you're making instant updates to acceleration decisions, and that's what we do. And so we used a bunch of obvious hardware and software components for this, connected to the OBD interface, and then connected to the gas pedal for this. Some of the data collection, we were using an Arduino board for certain actions. The actuation also went through the Arduino board because it was very useful to do it that way. And here is sort of the overall mess. But this is our gateway over here. Obviously, a lot of things are connected. The OBD device sending data. There's GPS to track location and all that stuff that's happening. And we tested this over a significant amount of area. Mostly with urban road segment because that's a little more easier. We had a controlled stretch of highway which is 2 kilometers long, and we were able to test this over that area. So we were able to demonstrate in various cases that you can get significant savings. Of course, depends on how good a driver you are. If you're really good with fuel efficiency somehow, we can't save much. But there was, we did test with at least 20 to 25 drivers, and we were able to see reasonable improvements in energy or fuel consumption by comparing the kilometers per liter and travel time of different systems. So we compared, human drivers, cruise control. Cruise control is also an automated system. The goal is not to manage fuel consumption, but to keep constant speed, or sometimes what's called adaptive cruise control, where you kind of keep a speed, but you can slow down depending on vehicles in front of you. So we compared all of them, and we collected a lot of so we did controlled experiments, and we also collected a lot of data in and around Madison, in fact between Madison and Chicago, from these vehicles, so we know what actually happens on the road, and then we can say what savings we can also accomplish on those roads. We didn't drive in all of these areas. We didn't drive into Chicago, for example, but we can, based on what we observe, we can see what potential is there for a much larger set of vehicles and users. So, for example, we collected data from at least 12 different vehicle types. Of course, this is not very scientifically picked vehicles. These are vehicles we had access to, or somebody had access to and were willing to let us instrument and collect data from. So you can see that on the columns over there are the number of miles these vehicles gave us data for, 1,000 plus miles in many cases. And so we were able to try this in different models. And the interesting thing to note is that the cruise control system usually, at least the ones we saw, they usually get to a certain speed faster. They try to accelerate to the right speed based on what a person wants to do. We tend to be more conservative in adjusting speed, and this gives us the fuel savings that we see. And you see a gap between the green line over there and the red line, and that gap is sort of think of it as a savings that we are able to accomplish over time. And the other thing also is apparent. This is time and kilometers per liter. So higher kilometers per liter is better. So as we should expect, since we are cognizant of fuel consumption, the green circles are eco-drive, and so we have higher kilometers per liter. Human drivers tend to, in this, at least the set we had the lowest one. Cruise control was slightly better, but it may not always be true. And you can see that most of the time, eco-drive took the longest because it's trying to optimize fuel cost as opposed to minimize time to destination. So you trade off something, and that's the trade-off we have, and it gives us some nice advantages. So those are sort of the observations we had made. Okay, so that's the second example I wanted to share with you. The third one, in my opinion, is sort of the most controversial. These two seems reasonable that you should and can do it. The third one, whenever I bring it up, people say that's the most stupid idea I've ever heard. So I'm prefacing you. You can still say that, but that's fine. And this is an example which I think is can be very interesting in the context of autonomous driving. Okay, so autonomous driving is all the rage. Everybody is trying to do it, and there are high-profile projects. One of the challenges of autonomous driving, and you can't read this probably, but it says augmented autonomous driving with remote support, and I will explain what I mean by that. No system can be perfect in the presence of conflicts. So autonomous driving systems, they're good, but there are problems, and we cannot always predict what they can be. And some of these may come up as funny examples, but not all of them. Like, if you come to a point, suddenly you see the sign which says road closed and local traffic only. What does the autonomous vehicle do, right? Should it make a U-turn on oncoming traffic and go? That is also not an allowed rule, but it says local traffic only, so you're stuck. What should that autonomous vehicle do? At least its rules are not there to figure it out unless you planned ahead, unless you anticipated this, right? So you may be stuck in this scenario. Sometimes you could have some complicated detours that the autonomous system may not figure out how exactly the detour is working. A human driver can look at it and figure out where I should be driving, which is the actual lane, even though it's not perfectly done, right? Especially in various working situations, lane markings are not obvious, and so an autonomous system may get into trouble. And once in a while, systems can malfunction, right? If your red light and green light are both on because your system malfunctioned, what should that car do at that point, right? An autonomous system will totally give up. And not the fault of the system, it's based on examples that we can provide to the system. Again, a human driver, I think all of us can assume that we will figure a way out in this case, right? We know what is the right thing to do, what is acceptable, what is societally or socially acceptable, and we'll take some action and we will get out of that situation. But it's harder for autonomous vehicles, at least today. So there could be others. And so what we proposed is have a backup. Now, the common backup people, casually if we say, okay, the first thing that comes to mind is if the autonomous function fails, give control back to the driver, right?
Now the problem is that if you're not paying attention because you're an autonomous vehicle, you're reading a newspaper, you're watching a movie, I don't know what you're doing, sleeping, and the car says, oh, take control, it will take you 20 seconds to figure out what's going on before you take control. That may be too late in certain situations, right? So it's hard. So the proposal that we had was to return control not to the local driver who is not expected to be paying attention, but to a remote driver. Imagine a call center full of drivers. All they do is they're waiting for something to happen and take control. They're trained, they're specially trained, and hopefully they're not having to do for every vehicle, but out of 1,000 vehicles, one has a problem, they take over for that vehicle, drive it to safety and let it go, and maybe autonomous function comes back and it's fine. Okay? So it sounds a little crazy that, I don't know where some remote place, somebody's driving my car, it's like a video game, but it's actually risky, and can this all happen? Well, I think there is not many other options. You can say that, okay, the car should just stop, but even sometimes that is dangerous, just stopping in the middle of the road. So at least the ability for somebody to drive it to safety or drive it to a point where it can then be handled in a different way may be something to consider. And so if you imagine that you can provide this capability, it can be a way forward for these kind of corner cases that are not predictable. So we did a lot of work. So with this premise, this is sort of justifying why we need that. Now, you may argue, whoa, that seems impossible to do with today's networks. You don't have the bandwidth necessarily all the time. You don't have the latency that you need all the time. Can you do this? So the rest of this work, this is actually a paper that appeared in Hot Mobile. So it was okay to be a little bit outrageous, and Giovanni was there, and we are now working on some more extensions to it. And even though we agree it's outrageous, I think there is some possibilities, and he's thinking of some more extensions to this. I think what we try to do is to see what can you do with today's networks. I think a good question to ask is, how should you design a network so that you can support remote driving? Right? That's a very different question. How do I provide guaranteed low latency paths for certain things, and how do I ensure that the latency between the vehicle and the remote driver is bounded so that you have the appropriate reaction times? You cannot make it unbounded, so that might automatically determine that your remote call center has to be within a certain distance of every vehicle, so you have to replicate this in many locations. It can't be one physical for the whole world or for the whole country. It depends on the distance. But this effort, we kind of focused on what can we do with today's networks, and we tried to come up with some mechanisms of encoding based on what's happening in the vehicle. If the vehicle's moving fast, we apply. So basically what you're trying to do is you're trying to send the entire context of the vehicle, the audiovisual context, to the remote driver, right? So imagery, actions, objects, ideally even haptic feedback to the wheel that he's driving on or she's driving on. So we focused on trying to come up with ways to reduce it based on the driving environment. If you're driving fast, you will do video encoding in a different way. You will apply FECs in a different way. And you could argue that, okay, you're kind of putting Band-Aid on current networks, and but we're trying to show that it can be done. Of course, it's only a little part of the story. I think the bigger and high-level question, so I will mention that we did some context-aware video encoding based on vehicular speeds, where you decide how many iframes you have based on how fast the scenery is changing and things like that. But I think, and we implemented this all with, obviously we didn't do it on real roads with autonomous driving, because I think I need more permissions and appropriate approvals. So we did proof of concepts in the lab using RC cars, remote control cars, using a Android-based controller and Arduino boards and everything, and then a remote driver sitting somewhere trying to control that. And we, it's all written up using C, C++ and some other stuff. In Java, we use OpenCV and other libraries for that, and we embed LiDARs and all this other stuff into it. And what we were able to do was to show, we experimented with different network latencies. So we obviously ran this mostly on Wi-Fi, but we kind of varied the latency of Wi-Fi artificially to make it higher, bigger, and kind of tried to scope out at what latencies is this not feasible, at what latency is feasible, so kind of provided some guidance and benchmark on what is possible. And basically the remote driver would be seeing the view that comes from one or two cameras, and they have a control, and they can drive the car and see how well they can do the actions, like go park it in this parking spot in the lab, and show certain functions. Okay, and so I think there is, what we did, I think, is mildly interesting. I think if you buy into this vision, then what can be done is probably more interesting. I think there's a lot of challenges in trying to design a network which can support this. The cloud infrastructure, the actual edge infrastructure, the wireless links and wireless technologies, and new technologies are there that can give you low latencies, but it's the end-to-end latency that is more challenging, and to be reasonably ubiquitous is even more challenging, right? And then figuring out how far a remote driver can physically be, and then we are very interested in building a scaled testbed for experimentation. In fact, one of my plans is when we create a large lab, which really we can put lots of these RC cars and obstacles and everything, and try out people's remote driving or even self-driving algorithms in that testbed, so that in fact I can use that for education too. So imagine you want to teach a classroom full of students on techniques for self-driving, right? You can't let them write code and try it out on the car on the street, but if you have a testbed of this type, they can try the different things, they can test it out, it crashes, yes, that's fine, next time it will be better, and you can iterate with different options around this. So we are actually very motivated to build this testbed at some scale, and with road signs and everything, and I think it will be a very exciting project just to engage with lots of students who can then play with these different algorithms. So in summary, I would say that the mobile vehicular edge or the roaming edge is actually, there's lots of interesting applications. I am actually engaged a lot with our local metro transit folks in Madison. They are very interested in all kinds of things we can do. We've been working on, there's a bunch of other projects where we are trying to track occupancy of vehicles using basically wireless signals by detecting people using using the RF channel, how many people got on the bus or left the bus. Can we estimate those, and from that automatically give them analytics on utilization, right? So these are lots of interesting things and opportunities we have to influence this domain. And there are very significant challenges too that we need to address if we want to make those things happen. But I think we can really greatly impact the transportation sector. Of course, things like autonomous vehicles and all are happening, but there is a lot more beyond autonomous vehicles. So I think building a good platform to support this vision, building some example applications using our platform or any other platform you like, and demonstrating them at scale, I think is challenging, and I think that's something that continues to excite me. So, Giovanni and I have been talking about ideas around this, and I'm very, very interested and happy if anybody else wants to participate or join forces with me, especially in both the machine learning side as well as the system side and network building side. So with that, I will stop, and I'm more than happy to take questions. Thank you.
I have a question.
Yeah.
I think for the summary, you're talking a lot about different applications and different domains. And the applications and domains you've shown have radically different requirements. Access to the car and the information that is available there. At the beginning, you were talking about a single platform.
Yeah.
To build them on. But then, these digress a bit, and they were all sort of using different sensors.
Yeah.
So, what's your vision in terms of getting to this single platform?
Right. So I think of the platform being the hardware is important, but the software framework that allows you to do different things. So we need to have the ability to bring many sensors and allow a stream from that sensor to be available and make it available to multiple shoots, as we call them, right? Each one can be developed by different people, but there's the same way of implementing the software. And all you do is you take data from different sensors, you do processing, there is a GPU available to you, you share the GPU, and you do your analytics using it. So that's the framework that I want to build. One application may only pick a few sensors depending on what it needs. But we will make all of them available, and you pick what you need, and you will utilize it to build your application. Now, the other critical thing here, we do this in Paradrop, is the issue around permissions. what, as a third-party developer, are you allowed to access all sensors? Probably not, depending on how sensitive certain things are. And so those are things that the platform or the framework should provide. And you will have to have a way to access certain information. You may not be given access to certain information, and then as a third-party developer, you can build this on this platform.
And you ever encounter a situation where like two applications will collide over the same?
Yes, I think there are many cases. I mean, especially, I can imagine we, of course, do, point examples exist. Like if some application wants to control the camera and you want to, pan, tilt, zoom, and two different applications want to do different things, that's obviously a problem. So obviously certain functions cannot be done by all applications and you should only limit them to others. So there is a big question about policies as to which application can do what, who takes precedence, and what happens when there is a conflict. We haven't really addressed it in a very careful manner yet, but we understand the issues attached to it. That's a good point. Yes?
So, about exchange of information between different vehicles, for example, what would you need in order to develop these applications?
You mean
so, because until now I understand that many applications have to do with local cameras.
Yes,
and
that's a good
perception of a vehicle its environment.
Yeah.
But what is the information we would need from neighboring nodes?
Right, that's a good question. The way I see this is we are building a platform on which you put applications. We can provide an interface through which you can discover nearby vehicles and communicate with them. What you do in the application is up to, say, a developer. You have to decide what data you want to share with the vehicle, but we can provide a channel to discover neighboring vehicles and communicate with those vehicles that are in the vicinity.
In the base of the data that you gather anyway in your own vehicle.
Yes.
So, yeah.
So there is another question. So I was actually in this workshop recently where we were talking about cooperative driving, which is another platooning and things like that. And one of the big challenges that come up is in terms of trust. Do I trust data that you provide to me? Right? That's actually why are autonomous vehicles autonomous and not more connected autonomous? That is, take data from somewhere else and act using that information. Again, autonomous vehicles tend to be single systems. They don't. Almost the assumption is that I don't trust anything else beyond what I can gather and infer, right? So once you let two vehicles interact, share information, the question that automatically will come up is what do you trust that come from another vehicle? Now, if they're all the same manufacturer, maybe you trust each other because that's who the software sort of provider is. But if they're different manufacturers or things like that, then it becomes complicated. But at least in the platform that we are building, we are kind of agnostic of that. We are providing a pathway for you to communicate, to discover, and then as a third-party developer, you decide how you treat data that comes from different vehicles and operate on it. In certain applications, it's okay, it's benign, because if you're doing driver analytics, if there's some bad data, you can live with it. Of course, if it's all bad data, it's a problem. But if it's safety critical, you can't do that. So I may not have answered your question, but I think this is a big interesting point.
And how much data can you save in each vehicle? That means, I guess all these cameras and all these operations, they have a massive
huge volume of data. So
yeah, exactly. So is there a specific window that you cut off or that you consider?
So in individual applications, it depends. But most of the things we are doing are all real time. So our goal is not to save data. Of course, if your goal is to save data, that's a different thing, and the limits are.
Because you're saying that by experience you learn some. So basically, you just do some kind of updating of.
Are you saying when we did an experiments, we of course saved data and analyzed.
After that, you basically adapt the system.
Yes. So
it's offline completely.
Not some. Eventual system is online, but when we designed the algorithms, we had to do a lot of offline. We collected data, we analyzed it, we decided which algorithms will work. What computation can I fit into my compute platform is also something we have to decide. You can't do a very complex CNN depending on what you're.
Yeah, but when there is an accident, for example, you should be able to record it.
Absolutely. So you could. So for example, if you're kind of doing incident response, what you could do is, you can take IMU sensor data. You know that this is potentially a bad incident because that, and then you save only that fragment of the video and archive it, and maybe only those snippets get uploaded to a server and nothing else, because anything else is probably not an accident information. So it actually reduces a whole lot of data that you need to upload. Otherwise, you're blindly uploading everything. That's very
You mentioned a problem with like permissions, and because I think it's a murky thing. Who is the user of this platform? Because you speak about developers, you speak about the people interested in the data, you speak about vehicles needing input from other vehicles, but I mean, certainly it's not the person in the car being in charge of like managing what the car is doing. So it is quite hard to understand who should be allowed to do what.
That's a great point. In fact, I'll give you the analogy. I mean, we haven't addressed it too much yet in the vehicular context. We have at least tried to address it in the home context. When I said that I have Banerjee that works in the home, it's a gateway on which third-party applications sit. So I think we identified at least 4 stakeholders, right? One is, say, the home owner, okay? Second is the user, which may or may not be the owner, right? So for example, maybe kids are not owners, but they're users, or maybe friends of mine are not. So there's second. There's a third-party developer who's actually built the application that's sitting. And the fourth is sort of, you can think of it as the provider. So in the home case, maybe the provider could be the ISP, okay? So depending on the context, some of them may be the same, okay? So the permissions, they depend on, who is allowed to make certain decisions. So there are these 4 stakeholders in the home, and it's possible to write down certain rules as to who needs to give permission for what kind of actions, at least at some level. In the vehicles, you may have an analogous thing, where there's a vehicle manufacturer, there's a driver, maybe a vehicle owner, and there could be a fourth, which is sort of the environment, and that's a little bit murky, in particular murky, because I don't know who that is in some sense. So I think that's something we need to still figure out. But for the applications we are developing, we tend to be very privacy focused. We don't store or save anything, especially anything identified.
Going a bit down in the details, the architecture seems to be kind of classic from an operating system point of view, which means that you get like containers which are like processes with a bit of isolation in the kernel. I was wondering whether you needed any sort of special facility to handle a lot of data, for instance, what's coming from cameras or high-speed interface or kernel web pass or like all this kind of stuff that is perhaps relevant for certain like particular.
Yeah, that's a good question. We haven't, again, these are all very early stage projects I'm discussing, so I think, I think those are some of the questions we are also asking ourselves. In fact, another example I'll tell you, in fact, we did with this kind of an infrastructure is actually city-scale spectrum sensing. So just as this is used for transportation, imagine that I want to embed all these gateways with wideband spectrum sensors. Okay, that's sampling the spectrum across very, very wide swaths, going from a few tens of megahertz to a few gigahertz. And I want to observe utilization and other properties. It can easily generate a huge amount of data, and again, from that application, we are trying to answer questions like, are there certain spectrum violations in certain parts of the city and who they are and all that stuff. So again, there's a question about how much data is coming in, what mechanisms we need, and here, for example, we are taking IQ samples or something, just power measurements. So I think these questions need to be addressed, and we are still posing them ourselves also. So if you have some thoughts, I'd love to hear. Yes.
So for the idea of the driving car, like the remote call center to drive cars, I was wondering why not have the car learn what to do in these situations. So say the car is sharing it with human drivers, it could see what the human driver are doing. But so the idea that's stuck in my head is like, if you have many autonomous cars in that situation, how many people in the call center do you need to handle this?
Good question. So if you're saying that the bad situation occurs for a lot of cars, then you may be running out of autonomous remote drivers, and that's a classic problem with sort of statistical multiplexing, and it doesn't solve it, but it makes it smaller perhaps. I agree with you that maybe once a human driver sort of shows the autonomous vehicle what it did to fix the problem, maybe then the system will learn. So it learns these new examples in that way, but how will the human driver show this autonomous system what needs to be done? It probably still needs to be a remote driver because the local driver is not really available. That's my point. But I think you're right. I mean, it doesn't guarantee anything, because if I have 1,000 remote drivers and 1 million cars, if there are 1,001 cars is the problem, we have.
My question is about the stakeholders, and I wonder if you include the stakeholder Big Brother in your schemes, because thinking about this invasion of privacy in the home and in the car.
Yeah,
It's getting intolerable. Really.
That's true. We kind of think of that I agree. I mean, we didn't think of that person as a stakeholder because we didn't think they're a stakeholder, because this data is all decided between these four entities in the home, at least in our context. But
you did mention insurance companies. So
right.
I mean, how do they get the data? And then if the insurance company get it, so can big brother.
Right, but they get it because one of the four stakeholders is partnering with them, and these four people completely own the data, and some of them can have complete control or not, and anybody else will only get access if they are working in some way with somebody among the four key people. So yes, they can get control, but they get control because somebody is explicitly giving them access or control, at least in our model. So I think there is risk, but I think if done right, you can at least decide to not give any data to anybody else because you have full control. Assuming no bugs, no things like that. Yes, sure. But good point.
I guess insurance companies in the US are already giving like devices to drivers to get the data, so this might be just like vector data.
Sure, and people obviously understand they're being monitored. So obviously you're giving up something, and some people are willing to give up privacy, others are not. And I think the insurance companies are saying, you do this, we'll give you a discount. So it's up to an individual which way they want to play. They can choose to not give data, and they don't get the discount. And I'm sure there's a regulatory piece too that will come in. So that's beyond my level of ability to talk in this context. But I think that's a piece. Okay, if not, thank you again for coming.